we still did not know how much these actually repel and attract each other, these charges. We know that likes repel, unlikes attract, and so on. But what is the exact amount? So there came this scientist called Coulomb who made it his work to actually figure this out. He did very meticulous experiments using something called a torsion balance. So you have this thing on your ceiling, you hang this string from your ceiling, and on the end of the string, you put a rod, a rigid rod, and on both sides of this rod, you put giant spheres, giant metallic spheres, identical, sorry, something like this. And then you bring in some charge. You bring in some charge, say positive charges, and since there was no way to measure these charges, you don't know what the amount of charge is. There is no way to measure at that time. So you just put some charge on this sphere, and put an equal amount of charge on the other sphere. How can you do that? How would you accomplish this? So
By oh,
yes, go ahead.
um, like there is conduction, induction, and this right friction.
Hmm.
So to apply just to have positive charge in the metallic sphere, we have to um, wait. Please explain, sir.
Sure, sure. So we want both of them to be equally charged.
Yeah.
It's easy to put one kind of charge. So people have figured out that let's call this one positive. It's just a convention. Let's call this positive and let's call
Okay.
this negative. So maybe the glass rod they started calling positive. So it's fine. So you put the glass rod in contact with these metal spheres and some of the charges get transferred. That's good. But how do you put equal charges on both spheres? So people figured out that symmetry can help you here. If you take two symmetric metal spheres and then you put some charge on this, doesn't matter what amount of charge, say capital Q, and then you bring the other sphere which is uncharged and you touch it with it, or you connect them with some wire. What happens? Some charges will start flowing
Yeah.
from this sphere to the other, because positive charges they don't like staying together. They repel each other.
Yeah.
So some of them will get transferred to this so that they are as apart as possible. And how much would it transfer?
An equal
In
amount with
an equal
the
amount.
with the first sphere.
Exactly. If these are identical spheres, it must be an equal amount because the charges don't know which sphere is which. They see the identical situations on both sides, so they'll equally distribute themselves. So this is a great way of using symmetry. So now you have got a q by 2 and q by 2 charge on both spheres. And now you can bring both spheres and touch them, touch one to this one, touch the other one to this one, and so you'll have a similar equal distribution of charges on both these larger spheres. So that was accomplished like this. Now, what they did is they brought some other spheres, some other charged sphere close to one of them. What does it do? It produces a torque on this whole system. So this starts rotating in this way. And this rotation causes some torsion in the string, which is supporting the whole system from the ceiling. And this torsion, people had figured out by then, using classical mechanics, how this torsion functions. So they know how much angular deviation means how much torsion. And this torsion can be used, this angular deviation can be used to very accurately measure forces. So they can firstly use Q by 2 charge, then they can halve it again using another sphere, and then they can use Q by 4 charge. And using these different charges, they figured out what the kind of forces these charges exert on each other. So what Coulomb found is that the force is directly proportional to not the charge, but the charge squared. And he
Okay.
also found out that As he started bringing these spheres together, that it depends on 1 by r squared. It's proportional to the inverse of the distance between the spheres.
Okay.
So the closer you bring them, the more repulsion they feel. And he combined these two. He combined these two into one law, called it the Coulomb's law. So F should be proportional to q squared by r squared. And if you uh, remove this proportionality and bring in an equality, you get something called a proportionality constant.
Yeah.
So it becomes
So
kq squared by r. Hmm?
so in this one, k is equal to 1 by 4 pi epsilon naught, right, sir?
Exactly. So there are historical reasons why he chose this particular number. We'll come to this. There is a specific reason for choosing this. And then he was able to generalize this law. Now see, the both charges were same, so he could generalize this when both charges are different. And again he did some very meticulous measurements, and he found out that when both charges are different, the force becomes 1 by 4 pi epsilon naught q1 q2 by r square, where q1 and q2 are the charges and r is the distance between them. Now you might already know that force is a vector quantity,
Yes.
so it doesn't make sense to only tell its magnitude. You also have to know the direction of force to
Yeah.
do anything useful. Could be that the force is acting like this, or it could be the force is acting like this. So the magnitude doesn't really tell you much. You also need the direction. So what is the direction that he figured out? He figured
Uh,
out that this direction always acts along the line joining them, either
okay.
in this direction or in this direction, depending on the polarity of the charges. If they are the same charges, negative, negative, positive, positive, then they will repel and the forces act outwards. Whereas if it's attractive, the forces will be inwards.
Inverse. Okay.
So you can express this in terms of a vector. F force on 1 due to 2 is equal to 1 by 4 pi epsilon naught q1 q2 by r12 squared r12 cap. So this cap here, this signifies that this is an unit vector. And what are unit vectors? Unit vectors are vectors which have length 1.
Okay.
So r12 cap would be the same as r12 vector, but now you divide it by the magnitude of r12, so that its
Okay.
length becomes 1. And can you use Newton's law to tell me what the force on charge 2 due to 1 is? How is it related to this force?
Um, will it be negative?
It will be negative of this. Newton's third law. Good. So now that we know what the forces between any two charges is, we might want to apply this to a situation where we have multiple charges. So even in a very simple system like the atom, there are multiple charges in the atom. So you'll have to figure out what the resultant force on something is. And how do you do that?
Resultant force.
Mhm. Suppose you have three charges on three vertices of an equilateral triangle. Equal charges q, q, and q. And then at the centroid of the triangle, you place a small charge, small q.
Oh,
What force
I,
would it feel?
a centroid force. Something I have forgotten about it actually.
So the thing is, if you actually join these lines, they would give you the direction of the forces.
Yes, sir.
And since the situation, see, It's invariant under rotation of 120 degrees. If you rotate this figure by 120 degree, it returns to the same figure. Nothing changes. So the forces should also be equal. By symmetry, we can say that this force, whatever this is equal to this force, and this is equal to this force. All the forces must be equal in magnitude. Directions must be different, but magnitudes are same by symmetry.
Okay.
So this, what I did here is implicitly apply something called the superposition principle. What this says is, if there are multiple charges, we can just take two of them. We can take pairs of them, calculate the force using Coulomb's law, and then add to it whatever other forces it feels due to the other charges.
Okay.
So what this means is, you can only take any pair of them and figure out the force due to it. So that's what I did. So the total force must be the resultant of these three forces. By symmetry, you can see these three forces are symmetrically pulling it on all three sides.
Yeah.
You can also do a component analysis, x component, y component, and you'll find out that it exactly vanishes. The total force is zero.
Okay.
Okay, let us look at a bit more interesting problem. So we've got a situation like this. So here you've got a minus q charge. Here you've got a plus q by 2 charge, and here you've got a small charge, test charge q, on the same straight line. So the question is, if this distance is 1 meters between q and q by 2, at what distance must I place this small charge so that it feels no net force? So this is 1 meters.
What's messaging?
Could you give this a try?
Uh, so the remaining would be, it would be one or so.
How did you uh, figure that out?
Well, q the distance between the charges uh, are in what do you call it, from this midpoint are equal.
But the charges are not equal. See, this is
Oh,
minus q and this is small q. It could be something different.
okay. So
So you
then,
have to work it out. You'll get an answer which is in terms of q's. So it won't be a real number. It'll have variables in it.
okay,
So let me help you out a bit. What you do is you first calculate the force due to this first charge here. You'll
okay,
get some force on this due to this first charge. So if you assume that small q is positive, you'll get a force in this direction. Let's call this F1.
okay,
Similarly, the second charge here, you'll get another force on this direction, F2. And these two forces have to be equal and opposite so that
okay,
the total force is zero. Agreed?
okay. Yes, sir.
So now I can use Coulomb's law to find the forces. F1, this would be minus q by r squared, and r, the distance is, see, this one is x and this is 1, so this is x plus 1, total distance, x plus 1 whole squared. Similarly, F2 is q and q by 2 times distance from x to second charge to q is just x, so this is x squared. So now you can equate these two, q minus q by x plus 1 squared equals to, must be equal and opposite, so minus of q squared.
Why
Most
is it
of,
why is it q by 2?
because the second charge is q by 2,
Okay.
so this force will be calculated based on this second charge,
Okay.
q1 q2 by r square. So most of them cancel out. What you have is x squared equals to
No, x plus
2x
1.
squared or 2x plus 1 squared,
Okay, yeah.
or 2x squared minus x plus 1 whole squared equals to 0, or so we get two values of x. One is 1 by root over 2 minus 1. The other one is x equals to minus 1 by
Root 2
root 2
plus
plus
1.
1.
Okay.
So obviously it cannot be negative. Distances are not negative. So
So
this is
it's
the distance,
okay.
the first. So what this negative is actually telling you is you could have placed this charge on this side, here, somewhere here, and you would have found a point where this is also true.
Okay.
So this thing that we did, this is called equilibrium. And equilibrium is when the total force on something is zero. Now in Coulomb's law, we had seen that there was this constant here, 1 by 4 pi epsilon naught.
Yeah.
Let's look at that a bit more. This thing, epsilon naught, this is called the permittivity. Permittivity of free space. And then you had your charges q1, q2 by r squared. So this whole thing sometimes is just written as k.
Yeah.
Sometimes you'll find that some books use k. This k has a value of, you need the value of this to find out any action force. Now I need to, sorry, I am getting some feedback. Okay. So could you tell me what the unit of this is?
Um, if
How do you figure
I,
out?
I, I think so. It's something like um, something. It has meters in it, right? Oh no, wait.
It
Um,
has.
yeah, meters. Um, I
Suppose you forgot. Suppose you
yeah.
forgot. You don't
Okay.
know what the unit is. How do you figure this out? So any equation in physics, whatever the equation be, always has to be dimensionally consistent. What I mean is the dimension on the left hand side have to match the dimension on the right hand side. So you can just put in the units for everything else and this will just drop out of the equation. Let's see. So for force, you know it's newtons equals to, I don't know what this unit is. Let's call this x. For charge, charge has a unit which is called Coulomb.
Yeah, Coulomb.
So you put in Coulomb times Coulomb, two charges there. And bottom, you've got r squared. So this is meter squared. All right. So x turns out to be Newton meter squared per Coulomb squared.
Okay.
So this has to be the unit. Good. See, there was some talk about free space. So what? Why do we need free space here? What does it mean? It
Is
means
this
that this force. Yes, go ahead.
good? No, the free space means like the space between the charges of the object, like just in general the distance between the charges.
Mhm. this is the space between the charges, is devoid of anything else. So that's why it's called free space, in the sense that it's vacuum.
Yeah,
So
vacuum.
this force formula only works in the vacuum. If it were not vacuum, the force formula would change a bit. What you would have is F equals to 1 by 4 pi epsilon naught, and then there would be this epsilon r, which is the relative permittivity of your medium, whatever medium you are doing the experiment in, and then everything else would be the same. So in a medium, the force law would be something like this. So this is only in vacuum. So this permittivity, why is this called permittivity? Because this is the amount of force it permits in that medium.
Okay.
See, if epsilon naught were to increase, the force would get decreased
Yeah.
because the denominator something is increasing. So it's the amount of permission it gives.